Hi, everybody. So today I'm going to be doing a hands-on Driverless AI Qwiklabs. So if anyone's interested in following along, you can set up an account with Qwiklabs and follow the instructions. I'm going to give us about 5 minutes for everyone to get set up and signed in. And then from there, we're going to use Qwiklabs for all of us to do the same experiment together. All you need is a Chrome browser. So feel free to start signing up, and we'll go through a couple experiments together. And I'll just walk through the instructions, but you're going to go to the H2O.ai Qwiklab.com, and if you don't already have an account, you're going to click Join. It's going to ask you to create a new account with an email address. You're just going to confirm your email. You should get an email with the confirmation link. And you're going to go back to the Qwiklabs and log in. And then from there, we'll do it together. We're going to go to the catalog and click on the Introduction to Driverless AI 1 GPU. And we're going to go through the experiments. And if you're just joining, we're doing a hands-on Qwiklabs today, so everyone can try a Driverless AI experiment together. And this is the instructions for how to get an account set up. Just a quick check. Can I get a raise of hands of everybody who's set up the account? OK. How about anybody that wants to do it but hasn't set it up yet? OK, so let's give everyone else a few more minutes just with the instructions on so everyone's able to start. Should I act like no? Like natural? OK. And just another quick check of the room. How many people have gotten the Qwiklabs account set up? OK, great. And how many people are still working on it? No shame. OK, we'll give it another couple more minutes. And while we're waiting, just to get set up, can I get a kind of an idea of the room? So how many people are familiar with machine learning? OK. And anybody do it in practice every day? Do we have any data scientists in the room? OK. And any people wanting to get started in data science or beginning their journey? OK, got a few people. OK, great. Awesome. So today we're going to be working with Driverless AI, which is what Arno just presented. It's this product that does automatic machine learning. We're going to do a couple of use cases, and I'm just going to talk a little bit about the agenda while we're getting set up. So I'm going to start just giving a high-level overview of what machine learning is. And then we're going to dive into 2 experiments with 2 different use cases. The first use case we're going to do is we're going to try to predict if someone won't pay their credit card bill in the next month based on their past behavior. And then the second use case we're going to try to predict if a loan won't be paid back based on things we know at the beginning of the loan. So those are going to be your 2 use cases today. We're going to walk through automatic visualization, model interpretability, and driverless AI experiment. And we'll also end talking a little bit about natural language processing. Okay. So with that, I think I'm going to get started on the introduction. I think everyone has this website, H2O.ai, and I'll bring it back up before we start again, in case anyone needs it. But let's get started. So I'm Kurka. I'm a customer data scientist at H2O, and I'm based in Mountain View, California. And today I'm going to be walking everyone through driverless. And I just went through the agenda, but the idea is we're going to try 2 different use cases today. With driverless, they're both supervised learning. We're both trying to predict yes or no. So yes, will someone pay their credit card bill, or no, they won't? Yes, will someone default on their loan, or no, they won't? Those are going to be our use cases today. And then we'll have some time at the end for any questions. So I just want to start off with what machine learning is. So our use cases today, the first one's going to be based on a customer's past behavior. Can we predict if they will default on a credit card payment? So this is, let's say, some information we've collected. We have information about what someone's been doing in the past, maybe some demographic information, and we want to use this for something. So that's a lot of the machine learning. We already have all this collected data. How can we use it to help us predict something in the future? So in this case, we want to try to forecast next month's payment. Who will pay, who won't? The other use case we're going to do today is based on the information known at the start of a loan, can we predict if the loan will be fully paid off? So is there information we can know just from the beginning when the loan is being created and agreed upon? Can we predict who will actually pay off their loan and who won't? And we're going to do both those use cases. But first I want to talk just about what machine learning is. So very simple use case. We have circles, we have green circles, we have red squares. Can we separate them in some way, right? And this is kind of like our use cases. Can we figure out who's going to pay their loan and who's not, right? We just really want to figure out the pattern. And that's all machine learning is doing. It's very flexible. So a lot of people ask, oh, is H2O specific to a certain industry? It's not. It's just a very flexible idea. This machine learning model is just going to mine the data for patterns to try to reduce the error of predicting some column. So it's just going to do everything it can to be able to predict a certain column. It's not industry specific. So in this case, hopefully, the model will find this pattern in my data to separate the circles and the squares. Now, this is a very simple example. It's going to get more complex, but can we apply this use case to our financial use cases today? So if we didn't know about machine learning, let's say we wanted to predict which loans were bad and which loans were good. How would we do it today? Just no machine learning. So maybe we think, is there a column in our data set or some feature about these people that I can use to separate them? And maybe some way to separate them that a lot of the bad loans are in one segment. So if I take a look at the interest rate of loans, it looks like the percentage of bad loans is correlated with the interest rate, right? So as the interest rate for a loan goes up, so too does the likelihood that someone won't be able to pay back their loan in full. So now just really simply, can I split the data by this? Right? So let's say we'll split it by 15%. We make a really simple decision, a really simple rule. If the interest rate is greater than 15%, it goes into my bad loan bucket. Otherwise, it goes into my good loan bucket. But this is a really simplistic rule. It probably has a lot of error. There are probably use case or situations where we'd be wrong a lot of the times. So what we can do is we can start going a little bit deeper. So let's look at the people with interest rate greater than 15%. And then let's take a look at another feature like income and see if we can, again, split the data based on income and get an understanding. Can we start segmenting the data even more to get a more, let's say, homogeneous segment where there's just good loans or just bad loans? Because that's really what we want. We want to separate them completely. We could also do the same thing on the left-hand side and maybe even mine into interest rate a little bit more. 15% was too broad. We actually want to get more specific. So what we just kind of walked through together was a basic idea of machine learning. But with machine learning, it's going to do this for us automatically. It's going to make much more complicated rules. And with driverless, it's even going to take it a step further. All we're going to do is give a data set and a column. It's going to try models for us, different algorithms, different parameters. And it's also going to add columns to our data set. So for example, maybe with my credit card use case, maybe a new column that would be helpful would be, what's the ratio of the bill paid, of the payment divided by the total bill, right? So something really simple. We could just add a column, 2 columns divided by each other. But Driverless is going to do that automatically and see if it helped the experiment get better accuracy. And that's a really simple one. It's going to do a lot more, and we're going to walk through it together as it's running. But this is the basic idea, and this is going to be automated machine learning. Okay. So with that, I'm going to just give a little intro to Driverless, and then we're going to jump into the Qwiklabs. Okay. So I know Arno gave an intro. I just want to walk through what we're going to be doing today. So the first step is we're going to put our data set in. It's going to do some data processing. It's going to detect what type the column is. Is it a categorical? Is it a numeric? Is it time? Is it text? It's going to do that all automatically for me. Then it's going to do some model and feature tuning. It's going to start to figure out which is the best algorithm, what's the best parameters, what's the first best set of features. And this is going to be an iterative process. And a lot of times data scientists will do this manually, and it's very time consuming. So we're going to see how many models Driverless is able to build. Our experiment should take about 6 or 7 minutes. The next step is feature evolution. Now this is going to start using a genetic algorithm to evolve those features. So how can we get even better features from our set? It's going to try different models and see how they perform, and use that information to guide the next set of features. Right? So is this feature doing well? Should we explore other features in that space? The next step is a final model training. Now this final model may be a single model, for example, XGBoost model. It may be an ensemble of XGBoost models. And in that case, it's actually multiple models put together. So the idea is one model is good, but more models are better. May have heard that in Aaron's AutoML talk. So it's going to actually stack these models together. And then the last step is it's going to create a scoring pipeline. Now, the scoring pipeline is something independent of Driverless AI, and it's used for productionizing this whole pipeline. Now, it's going to contain the logic of all the feature engineering. It's going to know how the model was created, and it's going to be able to take your raw record and score it. And we have 2 ways of doing that. One is a Python scoring pipeline, so it requires Python. And the other is a Java scoring pipeline, which we call the Mojo. All right. So with that, I think we should get started on our Qwiklabs, on our hands-on. So I'm going to go back to this first slide and just give everybody that website again, and we're all going to go to that website and log in. Okay, so let me. Okay, so can everybody, once, hopefully everyone has an account by now, can everyone go to this Qwiklab website? If you can, or if you're interested in following along. And if anyone's having issues, please raise your hand. We have people from H2O in the room that can come around and help. While everyone's getting up there, the data we're going to be using today, the first use case is going to be credit card data. And so we have some information about some demographic information about our customers. Now this is public data on the Kaggle dataset website. We have some historical pay status. So pay status would be, are they up to date on their payments? Did they miss 3 months? We have the amount they paid, and we have the bill amount. And we have all of this historical information for the past 6 months. And then finally, we have our response column, which is, are they going to pay their next month's bill? Okay. So pretty simple data, not that many columns. And we're going to see what Driverless does with it. OK, so I'm going to go now to my Chrome, and I'm going to go to Qwiklabs. And that's all. All right. OK, so here's my Qwiklabs catalog. And everyone, we're going to click on the Introduction to Driverless AI. Now, raise of hands, who's able to get to this catalog? OK, that looks good. So let's all click on it. All right. And what you're going to do is you're going to click Start Lab. Okay. And just to note, it's going to start it up. There will be right here a connection details with a URL you should go to. It should be setting up. You should see a green bar here. There should be some connection details once it's ready. And then there will be a license here. So this is in black. Once Driverless is up, it's going to request that you give it a license. There is a clipboard icon on the black license. You can copy it and paste it into the Driverless license when it prompts you for that. Okay, so I'll let everyone just get their lab, set it up, and we'll go from there. And again, anyone having issues, please raise your hand. And when you start it up, you should see something like this. You're going to say, I agree to these terms. And then you can put in a username and password. Any username and password is fine. And before I jump there, let's just see where the Qwiklabs are. Has anyone's lab set up yet? Still waiting? OK, so mine is up. I don't know about everyone else's, but if you should see here, there's a Driverless AI connection detail. So you're going to copy and paste that into a new tab on your browser. And let's all do that. OK. Now, can everyone give a raise of hands of whose lab is started? OK, great. So once you get here, please accept the agreement. And username and password, pick anything you want. Just remember it. OK. And we're going to sign in. All right, once you've signed in, there's going to be an enter license popping up. Now, if you can go back to the first page, the instructions page, and just click on this clipboard icon, copy it, and we're going to go to our Driverless and enter the license. It should give you this, save it, and now it should be, OK, your license expires in 1 day. We can just X that out. Anybody up to this part? OK, cool. OK, great. All right, so we're going to try to build a model. We're going to do it in 3 stages. The first thing we're going to do is we're going to just examine the data, get a sense of what we're working with. The second step we're going to do is we're going to build an experiment. And then the third step is we're going to interpret that model. OK. So let's say add data set. And we're going to go to the file system option. Now, Driverless does allow you to import data from the file system, from HDFS, from Amazon S3, Google Cloud, or Google BigQuery. Right now, we're doing Qwiklab that's running on the cloud, and we've already included a data set in this AWS instance. And we're going to click on File System, and we're going to go to Data. And we're going to go to our H2O World 2018 folder. So it's going to follow here, Data, H2O World 2018, credit card. All right, we're going to import our training data set. Press Import File. And it's going to be uploaded into Driverless. Now, right now, we're using an AWS instance with 1 GPU. It's going to be leveraged during our experiment. And we're going to add one more data set. We're going to add our test data set. So once this is done, we should have 2 data sets in the data set tab, train and test. All right. So the first thing we're going to do is we're going to take a look at the data. So everyone go to your training data set and click describe. It's the first thing that should come up. And when you click it, you're going to see a description of your data. Right? So this is some summary statistics about what your data set looks like. Very basic, just giving us an idea. So we have the demographic information, as I mentioned, education, marriage, age. We have some historical data. What was their pay status the last 6 months, their bill amount, their pay amount. And then finally, we have a default payment next month. 2 values, yes or no. The next thing we're going to do is we're going to visualize. So if you click on visualize, it's the second option. We're going to click on that and let it run. Now what auto visualization is going to do is it's going to automatically create graphs for you. Typically, exploratory data analytics is very brute force. We don't really know what we're looking for, so we're going to look at a lot of graphs and see what's interesting. Now with automatic visualization, it's going to automatically create graphs for you. The graphs that it creates are dependent, just going to refresh it, on the data set itself. So what you see come up for this one may not be always the case. Just refreshing it. Okay, so we're seeing here correlated scatter plots, skewed histograms, biplots, outliers, correlation graph, and so on. Okay. So these are all automatically created. You may see different graphs for different data sets. We're going to click on the correlated scatter plots first. Now, is everyone off to the automatic visualization? Okay. So let's click on correlated scatter plots. What this is going to show us is columns that are correlated to each other. Okay, so it's going to actually order it for us. Which ones are the most correlated? Take a look here. These are important to you. So we have here bill amount 5 is correlated to bill amount 6. What's that? That means the bill you had 5 months ago is very similar to the bill you had 6 months ago. Okay, makes sense. We're learning about our data. We can go carousel through this. The bill you had 3 months ago is very similar to the bill you had 4 months ago. Okay, we can keep going. Bill about 1 month ago is similar to the bill you had 3 months ago. So what am I getting a sense of here is that for each customer, the bill amount is very similar month to month. It's interesting to note that we're not seeing any pay amounts here. So the pay amount isn't correlated as highly. Okay, we're also going to take a look at the skewed histograms. So these are histograms, these are distributions of data that are skewed. So it's saying, take a look at this, this is an interesting distribution. Now the first one that pops up is the default payment next month. 0 means they didn't default, 1 means they did. This is skewed, there are a lot more people that pay their bill than don't pay their bill. Now this is pay amount 5, so it's also skewed. We can carousel through and learn a little bit about it. But the one I want to focus on next is outliers. So if we click on outliers, it's actually automatically going to find columns with outliers and highlight those outliers for us. So this is bill amount 4. We actually have 2 outliers. We have a couple of outliers that are negative. So the bill is for some reason negative. We also have a couple that are really high. So if we click on them, we can actually see what record this is. So this is somebody, 48. We got some bill amounts and so on. We're going to add linking and brushing pretty soon. That will allow you to edit the data inside the GUI if you want to change it. If you see that there's actually something wrong, it's not really an outlier, it's just an accounting error. Okay. We can carousel through and see these. Okay, so this is our automatic visualization tab. So it's just giving me a sense of what the data looks like. It's not unique to any use case yet. The driverless doesn't know I'm trying to predict default. We're just looking at the data. So now let's go ahead to our next step and run an experiment. So we're going to go to data sets again. We're going to click on our training data and click on predict. So it's going to be that third tab. Okay. And now we're going to actually build a model to try to predict if someone won't pay their credit card bill. The only thing you need to give driverless is a data set and the column you're trying to predict for. So we've already given it the data set. This is our credit card data set. And we're going to select our target column. which is going to be default payment next month. Now, this is all we need to give it. We're also going to give it a test data set, though. The test data set is something that we've manually held out, and Driverless is going to use it only at the end of the experiment. It's never going to use it during the experiment to evaluate models. It'll only use it at the end for your convenience, so you can see how well it does on unseen data. It's not going to overfit because it doesn't know about it until the end. The model's already been built. It'll just say, OK, for these new data you gave me, it's going to be 85% accurate. Okay. So we'll give it that test data. Credit card test. Now, there are a couple of other features. I'm going to talk about them in more detail as the experiment goes on. But I want to point out the experiment settings that Arno showed us in his previous talk. Now, accuracy is going to control the data size. The higher the accuracy, the more data it will use. If you lower it to 1, it may sample your data down to make it faster. It'll control the model used during the experiment. So right now, it's going to be using XGBoost. It's going to be using XGBoost. It's going to validate that model by taking 1/3 of the data out and holding it out as validation. And then it's going to have a final pipeline of an ensemble, 2 XGBoost models put together. Now, let's everybody try to up this to 10. Let's see what happens. Didn't really change. Any change noticed? So now, instead of doing a 1/3 validation split in the iteration period where it finds the best features, it's going to actually do 5-fold cross-validation. Now, this is going to take more time, but it's actually going to use all of the data. So the idea is it should become more accurate. So accuracy is going to take a little bit longer, but it could lead to a better outcome. And time is going to change the number of iterations it tries. So how many experiments does it try? How many models does it try? Now, interpretability is interesting. Interpretability is going to control the type of transformations or the type of new columns we allow Driverless to do. Now, interpretability, how interpretable is this data set that it makes? If we take 2 columns and add them together, I guess that's pretty interpretable. But what about something like truncated SVD, which is a statistical method that will reduce the size of your data? Now, that's pretty complicated, not that interpretable. So we're actually going to, if we up that interpretability, it's going to not use those transformers. So that's really dependent on your use case and your preference. Today, we're going to look at all the cool features that it will do. So we're going to lower that interpretability to 1. And it should give me all of the possible transformers. We're going to lower the accuracy to 6 today. And we're going to click on reproducible. If you want to follow along with me, I'm going to use reproducible. Right? It gives me a little bit of information about what's going to happen in my experiment. I'm going to click on score. That's going to be how do I measure the success of this model. Now, this is different scores for different types of use cases. If you have imbalanced data, you may want to use a different score. It really depends on the type of use case and what your business goal is. AUC is a pretty common one to use for binomial problems. We're going to use that one today. And we're just going to click on launch. All right. How many people have gotten this going? Right, that's OK, good. All right, so if anyone noticed, the first thing it said was it automatically dropped the ID column. So it knows the ID column is an ID. It's not going to use it during the modeling phase. So we're going to X out of that so it doesn't take up the screen. Now, we're going to get information about what's happening up here. It's telling me that it tuned 2 out of the 17 models. So it's in this model and feature tuning phase. And we're going to see iterations here. Each iteration is building multiple models. So here we have one model with different features. So this maybe tried a parameter setting that wasn't optimal for this use case, because we have lower AUC. So it's doing less well. Now, ideally, over the course of this experiment, we should see this iteration graph go up. We should see some improvement in our model. OK. The other thing I want to point out while this is running is you should see variable importance in the middle. Now, this is the variables that are the most important for predicting defaults based on our best model so far. OK, we're going to zoom in a little bit. OK, so some of the features I recognize, some I don't recognize. The first one is our pay 0. So that's the status currently, or status last month, let's say. Did they pay their bill last month? Are they up to date? Did they miss 3 months of payments? What's going on? Now, the second feature is something new. This is cross-validation target encoding. This target encoding is actually a way to represent categorical features in a different way. Arne was mentioning a couple of them, like one-hot encoding, frequency encoding, and so on. We're actually going to take your categorical features and figure out the best way to represent them for the model. So we see a lot of cross-validation target encoding, and we see some original features. And it's just updating. So if I zoom out a little bit, we're in the feature evolution stage. So far, it's been running for about 2 minutes. It's created 650 features, and it's scored on 22 models. And it's now in that genetic algorithm phase where it's going to evolve the features and figure out the best set for you. And they're going to start getting more complex. Okay. How's everyone doing? Is everyone's experiment going? No? Okay. If you have any issues, please raise your hand. Okay, so it should keep updating. You should see this keep updating. Because the best features are changing, it's learning the best way to represent it over time. Okay. Now, while that's running, I want to focus on the right side of the graph. We have an ROC curve. Anyone familiar with the ROC curve? Yeah? Okay, great. So this is telling me how good it is at separating the good from the bad. We can hover over different points to get an idea of the confusion matrix. And this confusion matrix is based on the internal validation data that Driverless created. So Driverless is doing an internal validation 1/3 split for validation, and it's showing me, for this particular threshold, which is about 17%, how many defaults do I get correctly, how many do I miss? You can look at these different locations. We also have a precision and recall graph. Now this is similar, except it's not showing the false positive rate and true positive rate. Instead, it's showing me the precision and recall for different thresholds. And the uses of these graphs are, Driverless is actually going to give me a probability that someone's going to default. But I need to make a decision from that probability. Should I say that someone's going to default if it's greater than 50%? Should it be greater than 20%? Now, these graphs are going to give you an idea of the best threshold. So if you want to optimize precision or recall, you can take a look at these different graphs and figure out which one for your use case is the best, which threshold. We also have lifts and gains, which is another way to show how well the model is performing. And in the final tab, you'll see GPU usage. So this is using one GPU, but it will work on multiple GPUs on a single machine. If you have multiple GPUs, you'll see rows of GPUs and their usage. All of the algorithms Driverless AI right now, the XGBoost model is GPU optimized, so it's faster with GPUs, and we're seeing it being utilized there. Now, it's built 11,000 features, 1,100 features so far, about 70 models. It's been 4 minutes. That would take a very long time, for me at least, to do by hand. So it's really evaluating a huge space of features and figuring out the optimal setting. Okay. Let's zoom in a little bit. Is everyone using the same settings, or do people try different ones? I don't know. Different ones? Anybody? Everyone use the same one? Okay. Okay, so here's our top features. It's still running, but it looks like it's starting to plateau, so it's probably going to start building its final model next. Now, the most important feature is something called cross-validation target encoding. We're going to talk about that. There's also some representation, numeric categorical target encoding and numeric two-categorical target encoding. So this is a little bit interesting, but what it's doing is it's actually taking columns that are numeric but have a low number of unique values and trying them out as both categorical and numeric, right? So if you have something like pay status, which is numeric, it's integers, -2, -1, 0, 1, 2, and so on, but it's not really a number, because -2 means they didn't use the credit card at all. -1 means they're fully paid off, 0 means they paid the balance. It's not really a number, it's more a category. So Driverless is going to try to represent it both ways and see which one does the best. And that's what it's doing right now. It tried it both ways. Okay, we're almost done. It says it's training the base learners. It's going to build an ensemble, if you remember. So it's going to build 2 XGBoost models and combine the predictions. And it's almost done. So while that's finishing up, I'm going to go to my slides. And we're going to talk a little bit about the features that Driverless created. Feel free to look at your screen at the model that it's running while we walk through these. Okay. So here's the features that were created in the Driverless experiment. This is the ones that I've kind of captured. The first one we said is the cross-validation target encoding. So we see that a lot, the CVTE. This is somehow important. It's coming up quite often. We also see some clustering features. So who here sees clustering in their experiment? Anyone see a clustering feature? Okay, some people. Okay, anybody see some truncated SVD feature? Yeah, okay. Anyone see something like categorical to numeric encoding? Should say something like cat, num. Okay, okay, great. Anyone see anything else? Curious in those features? Anyone see any interaction terms, like dividing, adding, subtracting? Yeah, okay, so we got a couple. So if you ran with different settings, you'll see different things. These are what I've captured with my settings. So let's talk a little bit about what these are. And 1 second, I just want to go back to my screen 1 second. Before I talk a little bit, everyone can see, once you're done, you're going to get a bunch of buttons. We'll talk a little bit about more of those buttons, but if you want to, you can click on Interpret this model, and we'll let it run in the background while we talk about the feature transformations that were done in the experiment. So once you're done, you can click on Interpret this model, and in the meantime, I'm going to be talking about the feature engineering. Okay, so we have these features. We got truncated SVD, we got clustering, categorical to numeric encoding, cross-validation target encoding. Who here is familiar with cross-validation target encoding? Okay, so I think one person. Okay, so it's a pretty new technique. It's a way to represent categoricals. Does anyone have any issues when they're building a model with a categorical column with a lot of unique values? Something like zip code or state or anything with like hundreds of unique features. Does anyone have any issues with that? Like, how do I represent it? Maybe the model's overfitting to that column. Okay, so that's a common issue. Cross-validation target encoding is one way to overcome that. Now, the idea is, let's not use the categories. Let's represent it as numbers. But how can you represent it as numbers? Right? Because they're not numbers, they're categories. Well, what we're going to do is we're going to replace the categorical value with the average probability of default for that group. So maybe rather than state, what's the probability that someone will default from a specific state? Now, to calculate the average, that's actually giving us the answer a little bit. Because to calculate the average, we know about the target column. So what we are doing is techniques like out-of-fold sampling and regularization to prevent overfitting. So basically, that just means let's calculate the average on a different data set than what we're going to apply it to. Just techniques to prevent overfitting. Now, let's give an example. We have pay status. Pay status 2 means they're 2 months delayed on their payments. Pay status 1 means they're 1 month delayed. Pay status 0 means they're up to date. If we take a look at our data, let's look at the people that have pay status where they're missing 2 months of payments. What's the probability of those people that they miss their next payment? Well, we might find that it's 30%. So now, instead of representing the pay 0 status as 2 months delayed, let's say 30%. Really simple. Now, what about the people that are 1 month delayed? So 1 month delayed, we look at the data, we do some mining, we find that 12% of them default next month. So we're going to replace all of the ones with 12%. And we're going to do that again for 0, which is up to date. So how many people, a percentage of people that are up to date end up defaulting? So 4%. So now we've taken our categorical column, which in this case doesn't have that many values, but think about it like zip code, something with a huge number. This is going to now be translated to numbers. And usually when I run an experiment in Driverless AI, these are one of the most important features in my model. So this is what Driverless is doing. You should notice that it did it for a lot of categoricals, not just the pay 0, but you should see it for a few. And you may actually see it for multiple columns together. So it may group by pay 0 and pay 2. And try to calculate the group bys of that. What probability for those combinations? Okay, so who saw clustering in their features? Anybody see clustering? Something that says cluster? If you go back. This is the ones I saw. I saw cluster TE and cluster dist. And just for your knowledge, if you do hover over the name, you should get a little blurb about what the feature is. So for clustering, we're doing clustering for 2 different types of features. The first is distance. So we're actually going to take the data, we're going to pick some numeric columns, and we're going to cluster on those columns. We're going to figure out the right number of clusters and all of that. So we have some clusters, we have some automatically generated. One of the features we're going to create is how far is each record to a specific cluster. Right? So maybe there's a cluster, a natural segment in my data set where people in this segment are likely not to default. The distance to that cluster will be very predictive for me. So it's going to do that. That could be a new feature. You probably maybe saw that. The other idea is, OK, we have cluster ID, but cluster ID is just a categorical column. So let's do target encoding on that categorical column. So let's take the cluster ID. We'll group by it. What's the probability of someone defaulting in cluster 1? What about cluster 2? And so on. So that's another feature you may see come up. OK. Now, if I go back to our experiment page, I'm just going to go back. Here we go. Let's take a look at the clusters that I got. Let it load. Oh, by the way, how many people's experiment finished? OK, great. And did everyone click on interpret this model? OK, excellent. So it should be running. But just so you know, if you want to exit out and see your experiment, you can do that while it's running. OK. OK. Am I not connected to internet? Oops, I am out off the internet, hold on. OK, here we go. So give me 1 second while I get back on, but here we go. OK, so for this one, let's zoom in a little bit. Now, the first cluster feature was a target encoding. So what it did was, a little bit hard to see, it clustered my data by limit balance, the pay status 3 months ago, and the pay amount 2 months ago. It clustered that into 20 clusters, and it's calculating the target encoding for each of those clusters. So something about their pay status, their limit balance, and their pay amount, these natural segments are important for predicting whether someone will default. Now, the other one is a different set of clusters, not the same one. It clustered by bill amount 1, age, bill amount 2, limit balance, and pay amount 3 into 4 clusters, and it's calculating the distance to one of these clusters. So it did this all automatically. It didn't need me to examine it and create the clusters for it. It just tried all of these features, and this was important. OK. Now, if you look at the right side, you should see a summary page once it's up. And we'll just look at this a little bit more. It's going to give me some information. It's going to tell me that it tried 47 iterations. The validation schema was 1 internal holdout, so 1/3 of the data was held out for internal validation. And it's created 1,346 features. But it only actually selected 55 of them. So it will do feature selection as well. Your final model shouldn't have hundreds or thousands of features. It'll do some feature selection as well, but it is going to try a lot. And the other thing we should notice is the number of models trained for each section. So it did 18 models for the model and feature tuning. It did 62 models for feature evolution. And it built 10 models for that final pipeline. And then we see the AUC in our validation data and the test. OK, so we're 0.8 AUC in our test data. And we can see here, these are some buttons. With Driverless AI, we can either score on another data set. So we can say, Driverless, score on this new data set I have and give me the probabilities. We can transform on another data set. What that's going to do is it's going to take your data and give you these features. So if you prefer to do your own model, you can do that. If you want the features generated automatically, you can say, Driverless, transform this data for me, and then I'll build my own model. And then we also have some Python scoring pipeline and Mojo scoring pipeline. Now, these are independent of H2O, or Driverless AI. It's going to be used for scoring. It doesn't need anything. It doesn't need Driverless running. And you can use this for productionizing. All right, so with that said, let's move on to the model interpretability part. So everyone click on interpret this model, and we'll go through this. So while everyone's interpretability is running, I'll just give a high-level overview of what's going to happen. OK, so model interpretability is the idea that now that we've built this really maybe highly accurate but very complex model, how do we understand what it's doing? Right? One of the keynote talks was about trusting the model. So this is the idea of, like, let's give an insight, make this black box model more understandable. with certain techniques for interpretability. Does anyone use any interpretability techniques right now or do any post-processing to understand their models? Yeah, like somewhat, right? Some kind of analyzing the predictions maybe, okay. So what Driverless is going to do is it's going to use a couple of techniques. There are two flavors. There's a global flavor and a local flavor. Global is going to give you a general sense of what happened. What's the general rules the model's following? What's typically happening? What were the most important features? Local is going to give you information about why a particular record had the prediction that it did. So why did this one customer have a high probability of defaulting? So it's going to become reason codes. We call them reason codes. We have a couple of different techniques. Now, what's the challenge here is that, first of all, our final model is two XGBoost models. Those are already complicated. But the data we gave it, we don't even necessarily understand, right? So how do I say, oh, it's because they had a high cluster target encoding when I cluster on limit balance and pay 3 and pay amount 2? It's not really interpretable. So what we're going to do is we're actually going to do something called a surrogate model. Is anyone familiar with the surrogate model or that technique? Yeah? OK, so something like Lime, that Lime is a surrogate model. OK, so what we're going to do is we're going to frame the problem like this. Driverless gives us this data. It gives us, we know the default, yes or no, and we have all of these fancy new features like target encoding, truncated SVD, and so on. What we're going to do is we're going to take the data, the original data, and we're just going to add a new column, which is what did Driverless think the probability of default was? So we have our original data and a probability column. And what we're going to do is we're going to take this data, and we're going to build a model on top of it. So we're going to build a model that's going to tell me why would Driverless predict this based on my original features. Right? So now from that, we're going to get variable importance just from the original features. We're going to get partial dependency plots just from the original features. We're going to get reason codes just from the original features. So I'm going to go through that now. In the model interpretability module, how many people's model interpretability module is done running? OK. So we'll start walking through it, and once you're done, please follow along. All right. So the first thing we're going to see is a summary. Is it OK? I'm asking now too late probably, but can everyone see? OK, because it's kind of dark. OK, so we're going to get a summary. This is just a summary of my model, the name, which was randomly generated, the validation AUC and test AUC, and how long it took to run. So it took about 7 minutes. And we also have the most important features. So we got target encoding at pay 0. We went through all these features. We talked about how they were created. What we're going to do, the first thing we're going to do is we're going to take a look at the Driverless AI model. We can look at the feature importance. So this is the same graphic we saw on the previous screen. It's the most important features based on the data that Driverless actually uses. But again, these might be a little complicated. How do we understand this feature? Right? So what we can go is to the Surrogate Models tab. The Surrogate Models tab is going to have a few different options. We're going to click on Random Forest and Feature Importance. Now what this means is we actually trained a random forest model, a surrogate model, and we built a model to predict the probability from Driverless. And from this, we're going to get feature importance. Am I connected to the internet? OK, so it should be up. So we're actually seeing the feature importance again, but it's my original features. So pay 0 is the most important, the current pay status. The pay status last month. Pay status 2 months ago is the second most important. Pay status 3 months ago. So the most important features are what did the person do last month? What did the person do 2 months ago? And so on. So without knowing anything about the time, the model's already picking up this idea that the most recent data is the most important. Does everyone see something similar to this? Yeah? OK. All right. So one of the issues with a nonlinear model like XGBoost is that we just know the variable importance. We just know pay 0 is important. We don't know what the relationship is with this pay 0 column and the probability of default. It's not like a linear model where we have a coefficient for each thing. So one of the things we want to do is get a little bit more insight. Like, what about pay 0 makes it likely that someone will default? What about the limit balance makes it likely that someone will default? So for that, we can go to something called a partial dependency plot. Is anybody familiar with partial dependency plots? OK, so they're also in H2O core, or H2O3. And the idea is pretty simple. Let's take everyone's pay status and change everybody's pay status to -1. Now, if I change everyone's pay status to -1 and calculate their prediction, what's the average prediction? So if everyone had -1, which means they're totally up to date with their payments, their probability of defaulting next month would be 19%. Now, what if we change that so that everyone's was 2 months behind on their payments? Now, if everyone was 2 months behind, the average probability would be 59%. Okay? So now we're starting to get an understanding of the relationship between this column and the probabilities. And we can actually look through different features. If we click on limit balance, we can see that limit balance is actually pretty flat, but it goes up at the end. So someone with a smaller limit balance is more likely to default. Does anyone have an idea of why that would be? I mean, well, probably limit balance is correlated to the credit score, right? So maybe that's why. So we can start understanding the model, and does it make sense or does it not make sense from my domain knowledge. Okay. And then the last thing we're going to take, or maybe not the last thing, we'll take a look really quickly at the decision trees. So here's this decision tree surrogate model. What it's showing me is, let's just break up our data really simply into a 3-level decision tree. And let's see what the segments are. So if we take a look, this group on the lower right side is a segment where the average probability of default is 76%. So this is a really high likelihood segment. And if we look through the tree, we can see that these are people where their pay status was 2, 3, 4, or +4. So that means they're 2 months or more behind in their payments. Their pay 3 status is 1, 2, 6 or more, and pay 5 status is 2, 3, 4 or more. So basically, these are people that just haven't been paying historically. And they're falling into this bucket of a 76% likelihood of default. So we can take a look and analyze this tree and get an idea of these high-level segments of high-risk customers, maybe low-risk customers. But again, this is still a global view. This is still giving us just a general idea of what our data looks like. So let's move on to the local view. And just a show of hands, whose model interpretability module is done? Okay, everyone. It seems like most people that are following along. Okay. So we're going to go move to the K-Lime model. Okay, K-Lime is our variation of Lime. And we're trying to get this individual reason codes. We want to know not just generally what's happening, but why is this one person likely to default? Right? So why can this be helpful? Let's say we're trying to predict churn. If we know why someone's going to churn, maybe we can combat it. Right? We don't want anyone defaulting. So really the idea is, can we somehow prevent it or figure out what's going on? Okay, so what K-Lime does is it's actually going to, well, let's look at the cluster. So it's actually going to take my data and cluster it into 15 segments. And for each cluster, it's going to train a linear model. And the linear model is going to predict that probability. The linear model is really one of the most interpretable models around. When I have my linear model, I know exactly how the prediction is made. Okay, it's because 0.2 times column 1 plus 0.3 times column 2, and so on. And we're segmenting it into 15 clusters because the linear model may be a bad approximation, but if we look at a smaller area of data, it becomes a much better approximation. So we're going to look at a smaller area of data and try to approximate driverless with this linear model. And what we're seeing here is the model prediction in yellow. So everyone with a high likelihood should be in the upper right-hand corner. And we're seeing the K-Lime prediction, or the linear model prediction, in white. Now, if they're close to the yellow, it means it's pretty good at approximating. So let's identify somebody in the upper right corner. Let's look at somebody with a high likelihood of defaulting. Okay, we're going to click on just some random person. They have a likelihood of defaulting of about 82% from our driverless model. And the actual value is 1, so they did end up defaulting. So let's see why the model thought that. We click on it, and you can click on the Explanations tab. Okay, so here we go. We're getting reason codes. Okay, the fact that their last month, they missed 2 months of payments, increased their likelihood of defaulting by about 28%. The fact that 3 months ago they also missed 2 months of payments increased their likelihood by 3%. So it's understanding, again, the idea of recency. The more recent information is more important than what happened 3 months ago or what happened 6 months ago. And then the last one, we have some negative local attributes. So their limit balance is pretty high for this data set, and it decreased their likelihood of defaulting by about 7%. So actually, this person's a combination of positive attributes and negative attributes, and together they add up to this approximate prediction. So we can get a sense of why the model thought that they would default. We also offer something called shapely reason codes, and the shapely reason codes are based on the engineered features. And they're going to be accurate to maybe the 5th decimal place. So you're going to get actually very, let's say, close approximation of why the driverless model made the predictions that it did, but it will be based on the engineered features. Okay, so before we finish up this particular experiment, I want to point out that we do offer a scoring pipeline. So these reason codes have a scoring pipeline as well. You can insert a record and get the reason codes out. And that may be important for your particular use case. So not only do you want to know who's going to default, but you want to know why. And that's available here. Was everyone who got the model interpretability to finish? OK, great. So with the remaining time, we have about 20 minutes left. I want to finish one more experiment. We'll do it a little bit faster. And then I want to leave some room for questions. Okay? So with that, let's go to the experiment tab. Or sorry, datasets tab. And we're going to click Add a Dataset. You're going to go to your file system, and you're just going to click on those 2 dots. This is going to go back out one directory. And we're going to go to my lending club directory and click on Train and import the file. And again, anyone having issues with Qwiklab, please raise your hand. OK, and we're going to add one more data set. We're going to add the same thing, the test data. Now, this is just a little bit of background about this data set. We have some lending club data. This is public data. It's information about peer-to-peer loans. We know if they fully paid it off or not. And this is a column I made. I called it bad loan. It's a bad loan if it wasn't fully paid off. It's a really simple idea, but we're going to try to see if we can predict that in advance. OK? And just again, the data set is located here. Lending club, train, lending club, test. We're going to try to predict bad loan. And this data set's a little bit different. The reason I'm going to mention that is we do have date columns in this data set. So we know the date the loan was issued. And we also have a description data set, description column, sorry. So the description column is going to be the person's peer-to-peer description of why they need the loan for. So this could be a quick sentence. This could be a paragraph. It's actually natural language. It's text. But it could be important, right? So why someone needs a loan may indicate if they'll pay it back or not. And so we're going to actually let Driverless automatically handle this. Now, typically, has anyone worked with natural language before? Freeform text? OK, so some people. Typically, you can't actually put this raw data into a model. It doesn't know what to do with it. It doesn't understand strings. You have to do some pre-processing. But Driverless is going to do this all for us, and we're going to take a look at the features that it finds. Right? And the first thing we're going to do is do our auto visualization very quickly. So we're going to run that visualize. OK. So everyone should see something like this come up. We've already looked at it before. But I really just want to quickly look at the correlated scatter plots, because I did notice something interesting here. So if you click on the correlated scatter plots, we'll see, let's see, that this one is member ID and issue date are correlated, right? So the issue of the loan is highly correlated with the member ID. So what does that mean? Does anyone have any idea of what that means about the ID? I mean, they're adding maybe 1 to each ID, right? So it's actually like the first person is ID 1, the second person's ID 2. And I wouldn't have noticed that without this graph. I didn't even realize that it was time-based. So actually, member ID is kind of a proxy for time, which is interesting to note. And you may want to know that before you decide to use it or not use it. We can also see that ID is correlated to time. So for each person, there's an ID for each record, and each person has their own ID. So maybe the person has gotten a loan multiple times, but it is definitely correlated by time. So, yes? Sorry? The location of it? Oh, sorry, let me go back. So everybody, if you want to get the data set, it should be here. H2O World, Lending Club, train or test. Okay. So we did look at the AutoViz. We see that there's some kind of correlation in ID, which I wouldn't have thought to analyze. And we're going to click on predict. We're going to select the target column. We're going to try to predict bad loan. And just a little information, we have some information about the person asking for the loan, their employment title, their length, their home ownership, their annual income. We also have some information about the particular loan, so the interest rate and the grade of that loan. And we're going to try to predict the bad loan. We can give it a test data set. And I'm going to lower the interpretability again to 1, just so we see what features we come up with. And I'll click on AUC again. So this is the features I'm going to run it with. It's going to give me a little bit about what's happening. It's going to do XGBoost again, 4 models in the final pipeline. Okay, I'm going to launch the experiment. I'm going to launch it right now, but everyone can still see the settings up here. If they're a little behind, you can still copy them. They're right up on the top. Okay, so the first thing it's going to do is it dropped columns with constant or all missing values. So payment plan in this case is all constant, and it's not going to use it. So it's starting to do some detection of what columns it's going to do. The second thing it did is it automatically dropped my ID columns. Okay, it dropped ID, it dropped member ID. Is everyone like in the process of starting this experiment? Okay. All right, well, if you don't want to, we can go along with it. Okay? And one of the interesting things we're going to see is how does it handle that text column? But right now we can see up here, it's checking for the shift. Okay, now look here. Significant difference detected, oops. Let's go here. Significant difference detected between my training and my test data distribution for the feature URL. And it gives me an AUC. So what Driverless is actually doing under the hood is it's actually looking at your training and testing data and see if there's any change in distribution for any of the columns, and it's going to give you a warning. So in this case, the URL is basically like an ID. It's pretty unique to each record. And it picked up that it's totally different in the training and the testing. Now, how Driverless does that, it's actually going to build a model, and it's going to say, model, can you predict if a record is in the training data set or the testing data set based on the URL? And if you can, how accurate are you? So this is almost 100% accurate based on the URL. And it's going to do this for all of my columns, and it's a really good way to detect if you have any shift in your test data. Now, if you get this notification or warning, that's a pretty good indication that your training data set isn't representative of what you're going to score on. And it's a pretty big warning. So it's running. It's trained 6 out of the 9 models. It's in that parameter and feature tuning stage. And let's just take a look and zoom in at the models right now, or the variables right now. We have a little bit of a different top features. The first one is the target encoding. It's the target encoding of interest rate. So it actually treated the interest rate right now as a categorical, grouped by it, and did the target encoding. But it also treated the interest rate as a numeric. So it's treating them both ways and seeing which one does better, and both are important. Annual income is left the same right now. It's predictive. But we have something called the text target encoding of description. So this is actually taking that description, it's sentences. Let me show you a couple of examples of them. Here's a couple of just clips of them. It's not the full, but here's a couple of loan descriptions. So they are natural language. And what it's going to do, Driverless, is going to take that text and it's going to tokenize it. So each word is going to be separated from this text, and it's going to create a TF-IDF matrix. Is anyone familiar with TF-IDF? Okay, great. So basically, how often do I see this word in the particular record? How often do I see it globally? Now, what it's doing, though, is it's not just taking that TF-IDF matrix. It's going to use these TF-IDF components and see if they're good features, but it's also going to do one more thing on top of that. It's going to build a linear model. And the linear model's idea, or goal, is to predict your target column, to predict bad loan, based on just the TF-IDF components. And it's going to take that linear prediction and use it as a new feature. So here I wrote it down. You have some generated features. This target text TE, this is going to be training a linear model on the text components from TF-IDF and adding that prediction as a new feature. And now this is a very powerful feature. It's the fourth most important feature. So something about this description is really indicative of whether or not the loan will be bad or not. So let's just flip back to our experiment that's running. Now the other feature that comes up that's interesting is the year of the issue date. So it actually expanded my date into year. It's going to try month, day of week, and all of these different things. Little information like month or day of week isn't that important, but the actual year of the issue is important. Maybe that's picking up something in the general economy. And then it's doing just a general target encoding of the loan term, the loan amount, and address state. Okay, so interesting to note, if I run this with just a regular GBM, I don't do any feature engineering, state can be the top feature, the most important feature. But in this case, state is in the bottom. It's like the 15th most important feature. Does anyone know why that could happen? Why would state be so important if I left it as a categorical? The reason why is that the really complicated models can start overfitting on state. So it starts memorizing the data with things like state or postal code, and they become very important in the model, but they may not actually be that important. And we're kind of seeing that here because by transforming it into target encoding, it's not that important. Because it doesn't have the chance to really memorize because it's a number. It doesn't have that ability to really segment the data by that. So we're going to let it finish running. Let me just fix my screen. It's running. It's doing the feature evolution stage. We have an AUC of about 0.726. It's training our base learners, so we're almost done with it. I want everyone to let it run. Did anyone see any different features than I did? Anyone see truncated SVD? Anyone see additional text features? Not just text TE, something else? Yeah, we have one person? OK. So it depends on the settings. With this, I think we're going to end with questions, of course. But before I end, I just want to point out a couple of documents. So we do have a Driverless AI overview. And that's going to show things like the transformations that were used. Right? So how these transformations generally, what they do. And we also have a download page where you can try Driverless AI. We have a free limited license to try it out. OK. So at that, I want to pause and leave the remaining time for questions. Any questions? Yes?
Where do you see the number of models being built?
Oh, so that should be on top, right on top of this. But it's only showing it during the model building, like when it's, right now it's scoring on the test data. So you'll see it at the final end. So once it's complete, this will change from ROC curve to an experiment summary graph, where it will list everything it did, all of the models. And that it should come up in a couple of, maybe a minute or so. Here we go. So see over here? Okay. Any other, yes?
What if it's a large data set that doesn't fit into one file?
So right now, Driverless, as Arno mentioned, is limited to single machine, but it's on our roadmap to make it distributed. Right now, I would say probably the best bet is to sample it down so that it fits. I mean, if you can't fit it on the single machine, we can't use it.
So related to this question,
Yeah.
what's the largest data set that you have analyzed by, the team has analyzed by?
10 million.
What's the size in gigabytes?
So we do tests with about a 10 million record data set. 10 billion, sorry, 10 billion. OK, the variables, I think, are about 12. It's the airlines data. I don't know if you're familiar with that one, but it's public data set. I wouldn't say that. I think a lot of, do you want to answer that? Sorry.
Yeah, you can. You can load a much larger data set. Again, it depends upon different data sets. We have tried with data sets that are 10 billion rows and close to 30 columns. But again, the number of the size of the file that we are able to consume in driverless AI in every version is getting larger and larger. So it's not a toy data set, again, but you'll have to try and play with your own data set. Terabyte. Okay. The actual physical file size, I do not remember exactly, but I can come back on that.
Any other questions about maybe how to, yeah? The variable that what? How sorry, what? Oh, how do you identify the variable? Is this a variable that you want to predict? Oh, how do you have, okay, so you can, if you want to predict like a categorical or a numeric, how do you tell them that? Yeah? Oh, do you want to tell them the type of data? Okay. Okay, so for time series, what we would do is, this isn't really time series, I would say, but we would pick a time column, which would be, let's say, issue date, and that would indicate to driverless that this is a time series problem. And as Arno mentioned, it's going to do historical data for training, more recent data for validation, and it will do time series specific features like lags and moving averages. Maybe I'll get back to you after to talk more about your question. Anyone else have a question before we end? Yep. So we do recently, we're going to be adding TensorFlow models. Sequence to sequence, I don't believe at the initial version, but we will have deep learning models in the next version, which Arno mentioned in the alpha state. Yes? So the models are going to get out by the scoring pipeline. So you're going to end up with a final model, and you'll have two options: Python scoring pipeline or Mojo scoring pipeline. Yeah, and that's going to be the exportable scoring code. It can either, it'll take a record and give you the prediction, or you can use driverless to transform your data and see it or get the score that way. Yeah, okay. I think we have time for one more question, yes? I can't really hear you, so I'll come over to you after the talk, sorry. Okay, thank you guys. So with that, I think we'll end our Qwiklabs, and I'll be around all day, so if you have any questions, please come up to me and ask me. Thank you.